I know that it's Yom Kippur today. So maybe we'll be we'll have a few attendees, usual attendees, who will watch the video at some later time.
Can you hear any of the street noise that's going on?
A little bit. I mean, very, very quietly. Like I think I just heard a car, but don't worry, I almost barely heard anything.
Hi, Martin.
Hi, Peter.
Hi, Jamie. Thanks for doing this.
No problem.
Maybe just wait a few minutes while people get their coffee.
Sure, sure. All right, well, I think we should probably start pretty soon. I've got my eyes on the participants list, so if anybody comes in, I can just let them in. So today, we're very fortunate to have a new BHI incoming postdoc, Jamie Elder, who'll be giving a two-part talk. And today we will be listening to her talk about direct detection in gravitational wave astrophysics. And without further ado, Jamie, the floor is yours.
Okay, so this is a two-part talk in which I'm going to be, in the first part today, I'm going to be talking about the direct detection of gravitational waves. And next week, I'm going to shift focus a bit and talk about how those gravitational waves are then used in order to observe astrophysical phenomena. Okay, so to get started. So famously in 2015, the LIGO-Virgo collaboration detected gravitational waves for the first time. So this first event, GW 1509-14, they described as the first direct detection of gravitational waves and the first direct observation of a binary black hole merger. And at least on the surface, these are somewhat puzzling claims. So first of all, these are incredibly complex experiments. involving very sophisticated apparatus, and indeed a whole host of models involved in the measuring process. So in order to detect gravitational waves, there's a template library of 250,000 templates that have to be used in order to search the data. And so this looks sort of several steps away from what you might just sort of intuitively think of as being some kind of direct detection. And second, of course, black holes are not the kind of things that we usually think of as observable in the normal sense. And so to hear the binary black hole mergers being described as directly observed, at least at first glance, seems a little bit surprising. So today I'm going to be focusing on the first part of this, the so-called direct detection of gravitational waves. Right, so quick outline of where we're going. I'll start by giving a sort of brief overview of gravitational wave astrophysics. Since the audience here is perhaps a little bit different from the usual audience I'm presenting it to, I'm going to go through that introduction maybe a little bit faster and pitch it a little bit higher than I usually would, but apologies if most of the audience is falling asleep. I'll just try and get everything on the table. I'm then going to talk about a terminological controversy that arose within the LIGO scientific collaboration over this term direct detection and indeed direct observation, and what it meant, whether or not they should be using it to describe what they'd done. I'll then talk a little bit about some philosophical literature concerning things like detection, observation, and measurement, sort of try and tease apart some of the differences between these two things, but basically just having some kind of sense of what these are on the table so that we can then try and figure out what it means to call these things direct, so like a direct detection. And then finally, I'll try to give an account of what I think direct detection of gravitational waves is supposed to mean here. And I want to flag right at the beginning that I don't think that direct detection is going to mean the same thing in this context that it means in other contexts. I think it's quite clear that this term is going to be used differently within different scientific communities. And in some ways, as I'll say at the end, I think that LIGO is in a way sort of a special case in that it's kind of straddling different scientific communities. On the one hand, it's much more analogous to something like particle physics and the Higgs detection. And on the other hand, it's much more analogous to like a telescope and other astrophysics. Okay, so first, whirlwind tour of gravitational wave astrophysics. So the vacuum Einstein field equations admit wave solutions, that is gravitational waves. And this is most easily seen within the linearized theory, where essentially you take the Minkowski metric as a background and you have some perturbation, some small perturbation propagating on it. And so the H is going to be the gravitational waves. For a particular choice of gauge, namely the transverse traceless gauge, you obtain these plane wave solutions. And the important thing for the purpose of gravitational wave astrophysics is to understand the effect that these have on test particles. So if you have a ring of test particles and a gravitational wave is passing, the effect is to sort of periodically stretch and squish the ring of test particles. These boxes here, in the top box we have the plus polarization, and the bottom box the cross polarization. Now, in the proper detector frame, which is the frame that you can sort of intuitively think of as being set up by the arms of the detector. So you take some rigid rods and basically set up an X and Y axis. In that frame, you can basically think of the effect of the gravitational wave passing as being described as being like a force acting on these test particles. So it's deforming the ring. And for the purposes of my talk, we don't really need to think about anything deeper going on than Just thinking of it in these kind of Newtonian terms as the effect of a force on the ring. So the first empirical evidence for gravitational waves came back in the 1970s and 80s with the observations of the Hulse-Taylor binary and subsequent calculations based on these observations. So this is a binary pulsar, which is periodically emitting electromagnetic pulses that are observed here on Earth with radio telescopes. And by observing the changes in the timing of the arrival of those pulses, you can infer the decay of the orbit of this binary and check for consistency with the predictions of such decay. So in general relativity, gravitational radiation will cause the orbit to decay in a certain way. You compare that to the observations and thereby obtain empirical evidence that gravitational radiation is really occurring. But the first so-called direct detection of gravitational waves had to wait until 2015 with the LIGO interferometers. The way that these work basically is that you have this L-shaped interferometer, and at the end of each of those arms is a mirror, which is acting as a test mass. And the passing gravitational wave will cause those masses to move. You can think back to that ring of particles from before. And from the movement of those mirrors basically represents a change in the length of each of those interferometer arms. That induces, so you have laser light going back and forth in those arms, and when a gravitational wave passes and the mirrors are moved, you end up having a change in the time that the light spends in the interferometer arms, and thus an induced phase difference when the two beams are recombined again. And so a photodetector measures the light from those beams, and that's translated into strain data. So the data output from these LIGO interferometers looks something like this. This is a very small sample of the data surrounding GW 150914. And as I'm sure you can tell just by looking at it, there is a gravitational wave signal in this data. No, I mean, clearly like that, you often hear people say that, you know, in the case of GW 150914, it was a really strong signal. And so you can sort of look and see the signal there. But I just want to be a little bit pedantic and point out that that's really quite far from the case. Even if you were to plot this, the plot that you get is extremely noisy, and it takes, you know, several steps of data analysis before you can see something even sort of resembling a little blip. So yeah, this data contains a lot of noise, but also a gravitational wave signal in this case. This is just a sort of representation of how the noise in the detector varies with frequency. I'm not going to talk too much about this, but yeah, just to have a nice picture there. So the overall strain amplitude, which is what was measured in what was represented in the data, is the sum of the signal and the noise, so H and N. And the goal of, like one of the main challenges of detecting gravitational waves is precisely separating out the signal and the noise, especially when the noise is often sort of much larger than the signal. There's two main types of searches used by the LIGO-Virgo collaboration, one of which is a modeled search, using basically a template-based search using something called match filtering. The idea behind this is that you take the overall signal S, which of course is the sum of H and N, and multiply it by some known signal, some signal you expect to be there in the data, or a template. So take the overall signal, multiply it by take the overall strain, multiply it by the known signal H, and then integrate over some time period. And because we expect the signal and the noise to be uncorrelated functions, this has the effect of basically this first term here is going to increase proportional to the time that you're integrating over, whereas this second term is going to sort of be repressed and filtered out. And so you end up being able to extract a signal even when the noise was much larger than the signal in the first place. But it's important to recognize that this method relies on knowing the signal in advance. Obviously, in gravitational wave astrophysics, we don't really know when a signal is going to arrive or what particular signal is actually going to be there. So instead of searching for a signal, one particular template, you have to search for basically any signal that you expect could possibly be there in the data. So this involves a library of 250,000 templates. And the search procedure involves going through and searching for every single one of them, although of course it's made a little bit more efficient than that. There are also unmodeled searches, which involve searching for excess power in two interferometers at the same time. So if you're worried by what I just said about the modeled searches, that the observation of gravitational waves involves a kind of theory latedness, and that you can only see what you're looking, what you go specifically looking for in the data. You might have some of those worries assuaged by the fact that there are these unmodeled searches as well. That said, the unmodeled searches are somewhat less efficient at extracting the gravitational wave signals because they're basically just not specialized for the kinds of signals we're looking for. They tend to find the signal but extract it at a lower signal to noise ratio. And there are also some concerns about how you validate the kind of detections that you get from these unmodeled searches. So these unmodeled searches are pretty susceptible to false positives. Indeed, one of the key uses of these searches is actually to veto data that has major power spikes and glitches. So the point is that even with this unmodeled search, without knowing the form of the signal you're looking for, the fact that the unmodeled search has produced something, it's hard to say that for sure is a gravitational wave signal rather than some kind of noise transient if you don't already know the form of the signal you're looking for. Just to sort of give you a big picture before I move on, this is just a schematic of how the LIGO methodology works overall. So you have the interferometer, which interacts with the gravitational waves and produces the data via some calibration procedure. You then have these search pipelines, which I've just mentioned. Once you've validated the event, then you can shift to thinking about how to use that gravitational wave signal to make inferences about a binary black hole merger. Okay, so I've already spent longer on that than I wanted, but next I just want to talk about controversy that arose about how to describe the detection of gravitational waves. So the LIGO-Virgo collaboration describes the Hulse-Taylor binary as having demonstrated the existence of gravitational waves. This is in the sort of discovery paper. So they attribute the first detection to Hulse-Taylor and Weisberg. So what they reserve for themselves is the first direct detection, which leads to the key questions. What is it that makes the LIGO-Virgo detection direct? And whether or not this distinction that's being made has any sort of epistemic significance. So Harry Collins, in his book Gravity's Kiss, describes the debates that occur within the LIGO-Virgo collaboration over how to describe GW150914. Got some big quotes here, but I'm just going to give you a quick summary of the main ideas. This debate had some kind of political dimension. Basically, there was a concern that calling their detection the first direct detection might cause offense because of the implication that that made their detection better. I'm not really going to say any more about that. Because there is also this philosophical dimension. There are philosophical arguments being made among the scientists about whether or not what LIGO did constitutes a direct detection. So Taylor, perhaps unsurprisingly, doesn't see there as being an important difference between the Hulse-Taylor binary detection and the LIGO detection. In each case, you're not doing some kind of basic measurement with a ruler, and so it looks pretty far removed from what you should call a direct detection. Similarly, this unnamed scientist emphasizes the similarity between what's going on in the two cases. So they say, we saw some masses which happened to be mirrors moving under the influence of gravitational waves. And then similarly, it looks like Hulse and Taylor are seeing masses which happen to be neutron stars moving under the influence of gravitational waves. So what's the difference here? Nonetheless, in part in reaction to a collaboration-wide poll in order to sort of determine what terms to use, the LIGO detection was referred to as a direct detection within the discovery paper. And so this looks like a pretty good place for a philosophical intervention, because unfortunately, just seeing that they decided to use these terms doesn't give us on the surface much insight into what they mean or why the terms are actually being used. So I'm going to do a quick detour through three related terms that are often sort of used interchangeably but have somewhat different meanings before moving on to talking about what I think direct detection means in this case. So the key feature of detection is that it establishes the existence or presence of some entity or phenomenon. So it has to be some kind of empirical information gathering activity, but the goal has to be to sort of show that something really exists or is really present. And this is always relative to some kind of background knowledge or standards of acceptance of a particular community. So standards of acceptance within particle physics involve having a signal of 5 sigma. Standards of acceptance for detecting carbon monoxide are going to be somewhat lower because you're really much more concerned about a false negative than a false positive. And of course, direct detection can take many forms. So in the first picture up here, I've got somebody looking straight at a kakapo, which is a New Zealand native bird, directly perceiving it with eyes. On the other hand, in particle physics, something like the detection of the Higgs involves a really complex experimental setup and complex theoretical apparatus. Detection, it seems, can also involve detecting some kind of, not involve detecting the thing itself, but detecting some kind of downstream consequences of the phenomenon. So to use another native New Zealand bird example, the kia is a bird that is very fond of causing destruction to cars by ripping off the rubber linings of the doors. This is like a classic signature that a kia has been present. If you observe that this classic signature of kia presence, you might say that you've detected the presence of a kia, even though you haven't directly sort of detected the kia itself, but rather some kind of consequence of its presence. And of course, detection can take on a variety of purposes, from discovering a new kind of entity or confirming said discovery, to sort of the more mundane cases of simply locating an entity in a particular spatiotemporal location. So like smoke detectors, carbon monoxide detectors. There's, yeah, basically just interested in the fact that it happens to be in that particular system. Observation, on the other hand, so we've talked about detection. Observation is a sort of much more highly contested philosophical concept with views of what counts as observable or an observation, ranging from the very strict, where observation can only take place with the unaided senses, in the case of Van Trossen, to much more permissive views that expand the notion of observation to include scientific instruments. Now, I think it's pretty clear that this strict view of observation is going to rule out all of gravitational wave astrophysics as counting as observation. So in a sense, that's just not really going to be a live option for my discussion to come. So I'm just going to sort of take a permissive view and roll with it. And in particular, so Franklin 2017 is, this paper tries to give an account of direct observation in physics and uses this permissive view, particularly based on Shapere, in order to this. So I'm going to sort of take that framing and assume that some kind of permissive view of observation is okay here. Just to get Shapere's view on the table, because this is going to be what Franklin relies on. Shapere famously claims that the interior of the sun can be directly observed using solar neutrinos, but not solar photons. So the difference being that solar neutrinos are coming from the inside of the sun and being transmitted without any significant interference to some receptor on Earth, such that the state of the receptor is informative about the state of the interior of the sun. In contrast, solar photons are really only informative about the exterior of the sun because well, basically the sun is opaque to photons on the interior, and so there's no sort of passage of any photons from the interior of the sun to a receptor is going to be so interfered with that you the signal just sort of gets lost. And note that whether or not something counts as a direct observation on this view is relative to the state of current physical knowledge. And in particular, he talks about the theory of the source, that is like the target system, the theory of the transmission, how the signal gets from that system to your receptor, and the theory of the receptor. So in LIGO's case, that would be an interferometer. And then Franklin, 2017, applies this analysis in his discussion of direct observation in physics, and including the case of GW 150914. Last concept here, measurement. So in the last decade or so, a contemporary view of measurement has emerged as where measurement is viewed as a model-based inference. So you have some physical interaction with the system, and then some model-based inference from the state of your measurement device to some parameter within the physical system of interest. And a complete measurement outcome has to include a best estimate of the value of that parameter along with some well-motivated uncertainty estimates. Just some quick terminology here. The instrument indication is supposed to be the physical state of the measuring device. So something like a pointer position or a digital display showing a number. And that's sort of like the physical state of the measurement device from which you're going to be inferring a measurement outcome. And so then this measurement outcome is some kind of selective representation of the system. So you take some entity, you interact it with the measuring device, you get the measuring device ends up in some physical state that reflects the state of the system of interest. And then from the state of the measuring device, you make an inference about the measurement outcome. Now, Parker 2017 offers a further sort of a distinction between different more or less direct measurements. So on the first we have a direct measurement, which is one where the actual sort of the raw data, where you're actually just recording the state of the measuring instrument, is already a representation of the parameter of interest. It might be somewhat bad representation. You know, it might be that you need to do a lot of analysis before it's considered a good measurement. But nonetheless, at least that sort of initial value is representing the property or the parameter that you're interested in. A derived measurement is one where you have at least one additional layer of inference from this. So you take your sort of raw instrument reading, sort of raw data, and then you have to do some kind of symbolic calculation in order to translate that from representation of one parameter in the system to a representation of some other physical, some parameter of interest. And then a complex measurement is just one that involves multiple such measurements in order to obtain sort of more informative measurement overall. Now, well, both the LIGO and the Hulse-Taylor detections are going to count as complex measurements on this view because they both involve, so in the LIGO case, you have multiple detectors, and it's never the case that you're going to claim the detection unless you have measured gravitational waves in multiple detectors over a period of time. And so in that sense, it's a complex measurement in this view. Similarly, the Hulse-Taylor involves a series of measurements over a period of time, and then from the arrival times of those electromagnetic pulses, you're inferring something about the dynamics of the source system, and thus about gravitational waves. Yeah, so this is just a quick representation of how this works. You have the gravitational waves interacting with your measurement system. That measurement system produces this sort of raw output, which does represent the actual strain of the gravitational wave. But then you have this sort of further analysis in order to get the sort of final measurement outcome, which is thought to be a good representation of the gravitational waves and also comes along with some uncertainty calculations. Right, so having laid a whole bunch of groundwork, I'm now just going to briefly talk about what I take direct detection to be in the case of gravitational wave astrophysics. So it's really clear, I think, what the intuitive difference is supposed to be. This is supposed to be a contrast between the LIGO Virgo That's the intuitive difference. It's a little bit hard to sort of pin down.
Why don't you try turning off your video for your conclusion unless you need a slide, just because you're freezing and we're missing.
Okay.
Just for a minute, just so you can get your peroration.
Okay, well, I don't think I can share my screen, so.
Oh, you need to share your screen, okay.
I will just talk, and we will try and sort this out for next time. Oh, okay, here we go. Right, can you see that again?
Yep,
Yes.
We can see it.
Okay, great. Well, this is, okay. Well, I'm just gonna then briefly go through Okay, let me reset. So Franklin in 2017 tries to give an account of what direct observation is. And basically he says what I've just called sort of intuitive view, which is that the interferometers are interacting with the gravitational waves in the LIGO case, but not in the Hulse-Taylor case. Franklin uses Shapere's account of direct observation in order to try and classify a whole range of case studies, including the LIGO-Virgo case, and as a way of trying to sort of sharpen this intuition. So at some points in this paper, he emphasizes the lack of interference that Shapere mentions. So the fact that there's sort of a non-interrupted transfer of a signal from the target to the receptor. This, unfortunately, doesn't exactly help us much in distinguishing between the two cases for gravitational waves, I think, because, you know, in both cases you do have the transfer of a signal without interference. At other places, he emphasizes the number of inferences that are involved, and says that this must be some kind of sort of degrees of directness depending on the number of inferences. And again, I think that this is probably not going to be a useful way of distinguishing between the LIGO-Virgo and Hulse-Taylor case, because these are both extremely complex measurements, and it seems likely that actually the LIGO case is going to involve even more inferences than the Hulse-Taylor case, just because the measuring device itself is so complicated. You're relying on the full sort of all of these templates, and you need very extensive modeling assumptions about the kinds of gravitational wave signals that you're looking for. At another point, he argues that one other sort of option for spelling out Shapere's view he uses in the case of the Higgs detection is that it's the indispensability of statistical arguments in the case of the Higgs is supposed to make it indirect. Now, I can talk about this maybe more in the Q&A if you're interested, but it actually looks like the LIGO case would be classified as indirect on this kind of spelling out of Shapere's account, because the way that the validation of the events is done actually involves a very similar process for calculating a background of events from which the signal is supposed to be sort of standing out. It's also clear that these are not equivalent, and these three ways of spelling out Shapere's account that Franklin uses, I think, they're not equivalent, and none of them individually seem to satisfactorily play the role. So instead of using this account of observation like Franklin does, I think it's better to distinguish between direct and indirect detection in terms of measurement. So on the surface, Parker's distinction between direct, derived, and complex measurements looks very unhelpful, because both the LIGO and the Hulse-Taylor detections are going to be complex measurements. But nonetheless, I think it hints at a way forward. So in the intuitive picture, I said that gravitational waves interact with the LIGO detectors, but not the telescopes used by Hulse-Taylor. This, of course, isn't true. Technically, gravitational waves are interacting with both. So the sort of more careful thing to say is that the difference is in how the measuring process is being modeled. It's about how you model the interaction of the gravitational waves. The detector in the LIGO case, that's how you explain the gravitational wave detection, but the presence of gravitational waves plays no role in the Hulse-Taylor case. So what I want to say is that the LIGO-Virgo detections are based on direct measurements, and that the raw instrument reading, that is that that raw data, or at least calibrated data, does assign some preliminary value to the gravitational wave strain. In this case, it is in some sense representing the parameter of interest. Whereas in the Hulse-Taylor case, although overall a complex measurement, the individual, the Hulse-Taylor detection is based on derived measurements, in the sense that the raw instrument readings or the sort of raw data that they're obtaining doesn't assign any preliminary value to any property of the gravitational waves. They're measuring arrival times of electromagnetic pulses. And so there's a sense in which the LIGO and Virgo interferometers are being modeled as detectors of gravitational waves, while the radio telescopes used by Hulse and Taylor are not. I think there's a sort of fairly obvious objection to this, which was already implicit in what some of the scientists said earlier, which is that why not just model some of these things differently? In the LIGO-Virgo case, you have a binary system emitting gravitational waves and its orbits decaying, and some kind of physical interaction with the detector system ends up transferring information about that process into electromagnetic pulses, and that's what's recorded. And then you make some inference about gravitational waves in the causal past. Similarly, the Hulse-Taylor-Weisberg case, you have a binary system emitting gravitational waves as its orbit decays. This is transmitted into electromagnetic pulses, and eventually you make inferences about the gravitational waves. I think this is, this sounds a little bit silly. It sounds a little bit silly to model these things that way. You know, it might seem a bit silly to say, well, why not just take the Hulse-Taylor binary as part of your detector system? I think you are free to model the Hulse-Taylor binary as part of your detector system if you want to. But I think that there's an epistemic reason why it's not very normal to model say the Hulse-Taylor binary as part of the detector system. And basically, this comes down to how you establish confidence in your model of the system that you are dealing with. So in the case of detection systems or measurement instruments, you establish your confidence in how, and the fact that that is a good measuring device for a particular kind of phenomenon, based on interventions, calibrations. As one scientist within LIGO said, since we built it, that is the interferometer, we know exactly how it works. Versus in the case of the Hulse-Taylor binary, look, you can include the binary as part of the detection system if you want, in order to sort of make it nice and parallel. But you're not going to you don't have those same strategies available in order for establishing your confidence in your models of the binary system. Okay, so that's all I've gone through pretty quickly, and it's gotten a bit weird without the video, but I'll just briefly state some conclusions and give you a sense of where this is going next week. So first of all, I think it's clear that there are several ways in which the LIGO-Virgo detection is not direct. The reliance on a very complex measuring process, the reliance on the sort of heavily mediated, the fact that it's heavily mediated by models of gravitational waves that are also based on general relativistic modeling of compact binary mergers. These are all senses in which make it sort of a very model-laden observation, and in some sense, highly indirect. That said, I think comparing these the two cases, the LIGO-Virgo and the Hulse-Taylor, suggests a way in which the former but not the latter is direct. So basically, the LIGO case is based on direct measurements of gravitational wave strain. The interferometers are being modeled as detectors of gravitational waves. And I think that this, although it's not the case that direct detections are always going to be better than indirect detections, this does seem to be a distinction with epistemic significance, because justifying your model of the detector is going to be done in a different way than establishing validating models of some distant target system. But the really important thing I want to stress, because this is where I'm going next week, is that this distinction is really not going to carry over to the direct observation of binary black hole mergers. So although at the very beginning, I told you that gravitational waves are described as a direct detection, as directly detected, while and binary black hole mergers were being directly observed. Direct cannot mean the same thing in those two cases. That's, I was filling these two roles, and in a sense, it's analogous to two different.
Jamie?
So,
Jamie, you just cut out a little bit. Could you go back a minute?
sorry, this is a disaster.
Just go, you just cut out a minute ago. Just go back to a minute ago. Hello? Jamie? I think Jamie's connection is not great.
That would
Okay.
be a deduction in line with the observed data, yes.
Okay. Can you hear me now?
Yeah, now we can hear you.
Okay. Well, I'm sorry about this. This has been kind of a disaster.
No,
no, you've done great.
No, not at all.
No,
Just go back
great.
1 minute. You were on your final slide, and you know, we were all there with you until about a minute ago, 2 minutes now.
So my conclusions?
Yeah.
Okay, I'll just run through my conclusions again, and sorry for any repetition.
Yeah.
I think we got
You
most of it,
forgot to say-
actually. I
Sorry.
think we got most of your conclusion. We did understand that this doesn't carry over to the binary black hole detection, and we understood, you know, you were sketching out what's going to happen next time. So.
Okay, excellent. So, right, so I was saying that I think some of the confusion surrounding whether or not the LIGO case is a direct detection is precisely coming from the fact that LIGO is sort of in these dual roles, where as a detector of gravitational waves, it's much more analogous to something like particle physics, where, I mean, you have this very complicated detector, you have something that's, you know, in your detector system, and you're trying to prove that it's there. And there's nothing sort of intrinsically astrophysical about what's going on there. It's all sort of very terrestrially bound. And on the other hand, you have the LIGO observations of binary black hole mergers, which make it as an instrument much more analogous to a telescope, where you are, you have these gravitational waves that are being used to make inferences about a different astrophysical system. And in a way, I think that this makes it kind of a special case, and I think that norms from different communities about what counts as a direct detection are sort of both being perhaps imported here, and it makes it somewhat unclear what's meant. But in a way, at the sort of simplest way of saying what the difference is between the LIGO Virgo and the Hulse-Taylor case is precisely just that you have, in the LIGO case, you are detecting gravitational waves in a way that's much more like a normal experiment. Whereas in the Hulse-Taylor case, you're really doing something astrophysical, dealing with a distant target system about which you have no independent access. Right, and so next week I'm going to be talking about the model-dependent observation of binary black hole mergers and the challenges that arise there. And so having seen sort of how the detection of gravitational waves work, we'll be in a better position to see how the case of observing binary black hole mergers is quite different and leads to a whole new set of challenges. Okay, well, that's it. I'm sorry that my internet has been so useless today.
Don't worry. Thank you very much, Jamie, for a lovely talk. And your internet just cut out twice. Don't worry. So round of applause for Jamie. So the floor is yours. Questions, comments, please go ahead.
I had a question. If no one else does want to, Jamie, I really enjoyed the talk. Thank you very much. Please don't think it was. No, it was great. On direct this issue of direct and indirect detection, I've had a little conversation once with Bas van Frassen on this some years ago, and what worries me about this, well, I won't call it fetishization of the eyeball or the eardrum, for example, is that what we know now about perception is that to some extent, all human measurements, even direct ones, are indirect and model based. Yeah, so we use, Bayesian inference. You can replace someone's eardrum with an artificial one. You can do so. Things that we're used to calling as internal could be internal and external. So really, the distinction I think vanishes. Now that sounds like a very, a more relativist position. I think it actually strengthens. Although it looks as if it's retreating on what we mean by direct detection, yeah, I think it actually advances that barrier. It advances that boundary because it shows that the Van Frassen distinction is arbitrary in any case. Now, do you have I'd love to hear what you say to that. It's not an original. It's a well-known criticism of the direct indirect detection. But I wonder what you'd say to it now.
Right, so I'm completely sympathetic to everything you just said. And yes, I think that once you look into the details of how, say, the human eye works, it's unclear why you would take them to be sort of epistemically privileged in comparison to scientific instruments, which we have a much better understanding of in many cases, and are much more reliable. And yeah, and so in a way I sort of breezed past this sort of strict view of observation and mentioned it in passing without too much argument for why we should ignore it. But yeah, I mean, it's first of all not going to be very useful in trying to make any of the kind of distinctions that I'm interested in here. And I'm ultimately not that sympathetic towards it as being a sort of epistemically good way of distinguishing between different kinds of observation.
Okay, cool, thank you. So cats among pigeons on this one.
Hi. Hello, Jamie. Thank you. I could just follow up. Be interested to know, Tom is my supervisor at the University of York, and I'm someone who has been asked that exact question because I do Van Frassen in the concept of black hole epistemology myself, and I'm on the strict side of this, so I come on the other direction. The question I was going to ask you here really was, I know you just discarded the strict understanding of kind of Van Frassen's understanding of observation and so on, but I worry about what that leads to in future and where that could have issues with kind of the rest of, well, I don't know where we're going, to be fair, so I could be completely wrong here, but there are metaphysical issues in terms of kind of the broad ontology potentially giving yourself by allowing all these kind of macroscopic entities to be classed under as observable by human beings. And I worry that there are potentially metaphysical issues in a kind of broader sense, that your ontology is so broad that you're giving yourself problems as the project goes. I mean, I could be completely incorrect here, but that would be my first read, that's where a lot of science, in my mind, and physics tends to get a bit lost in the woods and can't see the wood for the trees effectively by broadening out its ontologies too much. And that's why the strict view comes back into play with regard to understanding observation. That's why I'm a Van Frassen disciple. What would your take be on that?
So I guess I'm not too clear on what kind of problems you foresee here. I mean, so in a way, the strict view, I think it's perfectly reasonable to have debate about whether you want to be extremely strict about what you count as observation and what kind of metaphysical inferences you're going to make, what kind of level of comfort you have with such inferences.
I can potentially re-ask the question in a way that's probably more understandable. The motivating understanding for why Franson has observation is so strict and why he limits it down to kind of the eye and the privileged ability to perceive and have a really good perception of objects in the macroscopic world and so on and so on and so on, is based on a desire to get away from the problems faced by being a scientific realist and the issues you face when you get self-contradictory within the cause of scientific realism. I worry that by abandoning that here, we're potentially leaving ourselves open to greater problems within realism going forward, the ideas of problems via underdetermination and so on. And I worry that the way that you're talking about observation here leads to these problems becoming greater when they don't really need to be considered in the first place. All these things are equally good if they prove theories' empirical adequacy. There's no need to distinguish between here or make distinction if we can still retrieve empirical adequacy from both sets of results. It doesn't really matter what's direct or indirect. All that matters is that we've got good science out. And so that's my concern. If you understand, kind of, it's from the motivations of Van Franson through to why I personally view observation in this very strict way. And sometimes I know physicists don't like the idea that they can't see through microscopes and it's not real or whatever. But that's why I take that view on the philosophical side. If you get my point.
Yeah. So put it this way. I think I do understand the motivations for wanting to take the strict view of observation, and but there's a sense in which you can, I guess what I would say is that if you take the kind of strict view that Van Franson puts forward, you're going to have to get off the boat of like talking about observation so far before you're doing anything like gravitational wave astrophysics that it's not going to give you the kind of resources to make more fine-grained distinctions within all of these kinds of sciences. And so, look, I don't really care if you want to say that this isn't really observation, but observation star. I'm interested in these sort of like further distinctions that you can make with an observation star, and what kind of epistemic significance there might be to those distinctions. Now, of course, if you are an anti-realist from way back, you're going to have a very different understanding of what astrophysics is all about. But I guess for the purposes of what I'm doing, it doesn't seem particularly fruitful to sort of engage with this sort of strict view of observation, because it just doesn't kind of have...
You can't answer the questions.
It's not the right tool for the job.
Yeah, it can't answer the questions. Yeah, it doesn't really allow the questions to be asked in the first place. Yeah, that's fair enough. Thank you. Was enlightening.
Any other questions, please?
Sorry, I just got a question in the chat, but I think it's a private message and I'll have to follow up separately. So.
Sorry, there's a question from Nora Boyd on the chat as well, Jamie. Can you see it?
Okay, yes. So yeah, some differences. Right. Yeah, and I think that's it's a really interesting question. In a way, I think it's kind of well, Nora's not even here for me to answer this, so I'm not sure.
You might just make maybe a comment next time when she's there.
Yeah.
But you could also, you're welcome to talk about this question as well.
Yeah, I mean, I think this is something that I'm very interested in, actually, because although I've sort of said that there's this clear sense in which the LIGO interferometers are doing a direct detection while the Hulse-Taylor isn't, You know, the LIGO interferometers are indeed extremely complex measuring instruments, and yeah, I think there are some definite epistemic concerns about how much you can get through the kinds of interventions and calibration that are available here. But you know, they do have some pretty fine control over the system. They have like a million different ways of measuring the state of the measurement system. Anyway, I guess it's just probably better to talk in detail to Nora with. Is that it then?
Any last minute questions, guys? All right. Well, if there are no more questions, well then we'll have to thank Jamie. We're all looking forward to part 2. Jamie, thank you for the talk. Don't worry about the 2 internet glitches. They really weren't that bad.
I'll have to see what I can figure out.
You know if it's your internet, if it's your Wi-Fi, or if it's...
So actually, I suspect it's actually because it's hot.
Right.
So the only time I've had problems recently is where I think my router is getting overheated. So I'll see if I can put it somewhere cooler.
Yeah, that's a good idea. But it really wasn't that bad. Don't stress out about that.
Okay.
All right. Bye-bye, everyone, and see you next week.
Bye.
Bye.